So, welcome to the last lecture of 67350. It's nice to see all of you guys, the few and the proud that actually come to the last lecture of a course like this. It's great. I'm honored. So, in terms of announcements and things at this point, hopefully by now you guys understand the cadence of this course. We do not have another quiz. We're done with that. Mazel. The only thing that's left is to take the final exam, which is a week from tomorrow, I think. So there are review sessions for the exam, but I've forgotten when they are. Okay. Monday, 5 to 8 p.m. There's a review session. I'm sure you can find the location on Piazza. Um, and I will continue to have office hours. I think you guys will too next week, at least the ones before the exam. Leticia says no. Typically we do. No? Okay. We will keep you posted whether there's office hours next week. But regardless, certainly mine will be on Wednesday, so I look forward to seeing everybody there. As you guys have probably figured out, like, what was that, Alicia? I think, oh, Tuesday. Yeah, sorry. My office hours for my other class are on Wednesday. Got it. Okay, yeah. So Tuesday morning, I will see you guys. In case you haven't figured out by now, like, I write the exam, so chances are if you want exam review, that's a good place to go for help. Any questions? Oh, and you can get 1 page of notes for your exam, double-sided, just like your midterm. Questions, comments, concerns? Yes. Exactly the same policy as the midterm. Yeah.
Can we use our midterm page and just add another page, or is it only
one? 1 sheet of paper. You can create that sheet of paper any way that you wish. Any other questions? Also, I mean, if you haven't figured out by now, creating that sheet of paper is mainly a study aid. Like, I think it's pretty rare to actually rely on the formulas on that page. Okay. With that, let's get started. So we have one last lecture left in this course, and then we're done with this course. So we're going to basically wrap up today by finishing off our discussion of ordinary differential equation integrators by covering one final integrator that I think is worth knowing because it shows up a lot, especially in the physics world. And then I thought for fun, we would wrap this course up by talking about a fun topic that I think actually manages to glue together every single topic in this course, which is how you might differentiate through a solver for an ordinary differential equation. So for instance, maybe I'm trying to solve an optimal control problem. I want to know like what force to apply to a physical system so that its configuration at time 1 has some property that I'm trying to optimize. Then I need to differentiate through a problem where the variable is maybe the initial conditions of my differential equation, but the optimization objective is evaluated at some other point in time. And so we're going to see there's a really beautiful method out there called the adjoint method, which can do this thing using a second ordinary differential equation solver, which is a little bit surprising. And by the way, there's a lot of different reincarnations of the adjoint method. You can also do it for differentiating through optimization problems with like linear constraints and so on. It turns out to have a very similar form. But we're going to do the ODE one because I think it links together a lot of topics in this course. And it's kind of a nice way to wrap up that isn't just doing Newton's laws, which is the typical thing that one does in a class like this. Okay, so to wrap up our discussion of ODE integration, essentially we got almost through our list, but there's one additional one that's worth being aware of. By the way, there's many additional ones being, I mean, anybody should spend a career studying these things, but there's one more that you guys should be aware of for your final exam at least. And that's one additional strategy for integration that I think is kind of nice because it still links us to some of the observations that we made in our numerical derivative lecture. So if you recall, the basic point of most of our previous lecture was to go back to one of the assumptions we made 2 lectures ago, where essentially we did this nice reduction, right? We showed that if we have an ODE of some high order, we can always reduce it to an ODE of first order by essentially introducing convenience variables. So an example of that strategy is shown on the board here. Let's say that I have a differential equation, which I'm realizing is not actually on the screen, so I'll write it down for you. I have some differential equation of the form y double prime is equal to f of t y y prime, right? So this would be a second order differential equation because the highest order derivative is 2. I don't think that's too surprising. Then essentially what we did 2 lectures ago is we introduced a reduction like what's on the screen. So we added a new variable v, which stands for velocity. And we said, well, there's actually kind of this interesting first order ODE we can write in the y comma v pairs, right? Which basically says d over dt y v is equal to v, and then f of t y v, like that. Now, to be clear, this is just a notational change. I mean, there's really nothing too exciting that's happened here. But it is true that we now have a first order differential equation, right? There's only one derivative here. That gives us solutions to our second order problem by introducing variables, right? And so why did we do that? Well, then we spent the rest of that lecture deriving different integrators specifically for first order problems. And in the back of our head, we know that, oh, we can still solve things like f equals ma by applying this reduction. Then in the previous lecture, we said, well, wait a second. We showed that we can solve problems that way, but that's different than should we? And in particular, there are other integrators that are very specific to the second order ODE problem. And those integrators have this, they tend to have this kind of interesting property, which is that we notice we don't need to integrate v and y with the same level of accuracy, right? And so the intuition here, just as a little bit of review, is when we put in this Taylor series, notice that there's this h coefficient in front of y prime, which means that if we have a pretty bad estimate of y prime, it's still multiplied by h, so like if this is linearly bad, then the estimate of y is quadratically bad, which allowed us to do some interesting things with our time integration. Namely, we could derive integrators where v is being advanced with a linear level of quality and y is being advanced with a quadratic level of quality. And that's sort of okay and consistent because of this h coefficient sitting there. Right? That was our sort of high-level consideration. And in particular, we derived in the previous lecture using what I would classify as a horrifyingly ugly, not particularly intuitive proof, a class of integrators known as the Newmark scheme. These are very popular in structural mechanics, which looks a little something like this. And essentially, by the way, if you go back and look at that proof, like it's technical, there's a lot of indexes, there's integrals and Taylor series, but it's not particularly advanced. It's just a lot of calculation. Really, it's just polynomials. But in any event, essentially what we argued is that any time integrator of this form, notice that this is sort of implicit, right? Like this is a way to get y and v at time k plus 1 given y and v at time k by solving this big system of equation. By the way, typically you eliminate a, you just plug in f in those two expressions. This is a system of equations to solve, and when I advance it, basically for any choice of beta and gamma, I get a different time integrator. Which is kind of cool. And so some of them, you can see, end up being implicit versus explicit. So for example, let's see, if I take gamma and beta to equal 0, then notice that, in effect, I've zeroed out these terms on the right-hand side, right? And in doing so, I think I've removed all of the things with a k plus 1 in them, and now my time integrator is explicit. On the other hand, we also showed, it probably passed by a little bit quickly in the previous lecture, that for a very particular choice of gamma, I think, yes, gamma, this integrator has higher order accuracy. So essentially, this is kind of like a nice cookbook for deriving different methods, some of which are implicit or explicit, some of which are high order, some of which are not. They have different stability radii and so on. So this is a sort of a quick mathematical shorthand people use to derive all kinds of integrators for physics problems. And fun fact, we proved at least facts number 1 and 2 in the previous lecture. It's second order accurate exactly when gamma is 1/2, which is basically a byproduct of our symmetry argument for numerical derivatives. Like when gamma is 1/2, we kind of like expanded a Taylor series right about the midpoint. And moreover, it generalizes a bunch of integrators. So for example, we showed in our previous lecture, for a particular choice of beta and gamma, you get like the trapezoidal integrator and so on. We did not show the stability. In fact, you can, I don't know, you can do that if you want. I'm not going to in this class. Enough already. So in any event, the Newmark class of integrators is one that's worth knowing because A, it's just like a giant class of numerical methods all in one, and B, well, B, it's a standard choice, and C, it's a quick shorthand to derive a lot of these things. Incidentally, I was reading through a bunch of academic papers, a kind of fun one. It turns out that all of the the Newmark schemes are also variational, meaning that they actually preserve momentum, which is kind of cool. So if you put in a physics system from Newton's laws it turns out that this thing, like a certain symmetry group, applies to this class of integrators, and because of that, there's actually conservation law. That one requires a little bit of proof, so we're not going to do that in this class. That said, there's actually all kinds of integrators for second order ODE, which is like not surprising because like f equals ma, it's been around a long time, and like people want to solve that. And this Numeric class is just one. In fact, it's fairly modern. I think it's from the 1960s or so. But there are other ones out there, and there's one additional one that I think is worth knowing because I think it challenges another assumption of our ODE integrators so far. So in our previous lecture, we realized that we can integrate y and v with different levels of accuracy while maintaining the high level of accuracy of y. Hopefully that sentence parses. But in fact, we can do something even sneakier, which is that y and v don't have to live at the same time step. They can actually exist at different points in time. And there's actually good reason to do that. And this is going to be the difference, for example, if you go on to take a class in partial differential equation, which you should because they're fun, between what we call co-located methods and methods that are, well, I guess not co-located. And in particular, recall that from our lecture on numerical differentiation, what did we show? We showed that essentially, you know, if I have my t-axis here, and I have some value of a function like f of tk, and f of tk plus 1, what can I do? Well, I can approximate the slope of this function by just, you know, doing like, you know, f prime, and I'm going to purposefully leave out the argument here, is roughly equal to f of tk plus 1 minus f of tk divided by tk plus 1 minus tk, right? And we showed that in general, this approximation, it holds to first order, right? Like in other words, its accuracy kind of depends linearly on the width of this interval. But notice, like, I kind of did something sloppy here. I didn't say f prime where. And in particular, it is a good first order approximation of the derivative of my function anywhere in this interval, right? That's basically, if you look back at our Taylor series argument, what we showed. But in fact, what we showed is it's a second order approximation of the derivative right at the midpoint, right? And that had to do with the fact that like there's a bunch of things that cancel in your Taylor series in the linear term, specifically when there's a nice symmetry. Yeah? And so because of that, that actually inspires a new class of integrators for physics problems that are still going to be based on this same reduction. But the idea here is that, let's say that I want yk plus 1 to be kind of like yk plus h vk. Then immediately I've kind of got linear error if I want to extrapolate in this fashion. So here's a kind of interesting observation. If I wanted a higher order integrator, why not stick the v's at the half-time intervals and the y's at the time intervals? Okay? So this is an idea called leapfrog integration, or actually it has a bunch of different names. Leapfrog, staggered grid, a lot of different things. And they're going to do the following. This is a really sneaky trick. There's so many sneaky tricks in this domain. So in the integrators we've derived so far, I'm going to keep drawing our little timeline t. Right? We have time t1, t2, t3, t4, and so on. And we've got a bunch of variables in our system. Namely, we have like the configuration of our system y1, y2, y3, y4, and then typically v1, v2, like that, right? That's perfectly fine. Like the numeric integrators, I mean, if you look back, essentially what do they do? If you look at the dependencies of these things, it's kind of like saying if I know these two objects, the numeric integrators tries to predict those two objects and moves forward in time like that. Now what we're going to do is a really fun new set of schemes called Leapfrog or staggered grid. We're going to say, okay, in some sense, if we do a divided difference of the y's to get the v's, then we should think of the v's as living at the half-time steps. So we're going to have like y1, and then v, I guess 3/2, and then y2, and then v 5/2, y3, oops, sorry, y3, v 7/2, and so on. Right, so we're going to just think of the v's and the y's as sitting at different points in time. Does that make sense? By the way, usually in order to use these integrators, you do have to do like one little half-time step at the very beginning to advance to v. That's a technicality. Okay, so how are we going to do that? well, here's a kind of nice approximation. I guess we already wrote it down, in fact. Notice that we can say yk plus 1 is yk plus h vk plus 1/2, right? And the good news here is that this approximation holds to higher order than our typical one because this v sits in the middle of that interval, right? Okay, moreover, here's a kind of fun thing that we could do. Let's put the accelerations back at the integer time steps, right? So you can see we kind of keep pinging back and forth for each derivative that we take. So in principle, maybe we also do an integrator that's similar. We say v k plus 3/2 is equal to vk plus 1/2 plus h a k plus 1. So this is exactly the same leapfrog formula, just with one derivative higher. Now, unfortunately for us, this turtles all the way down. At some point, we're going to have to actually evaluate the acceleration. And this is where things get a little bit tricky. Because typically, remember our ODE, right? So it's y prime is f of, double prime is f of t, y prime. Now there's going to be a problem, right? Because we want to be able to evaluate acceleration at some time. But unfortunately for us, now we don't have velocity and position at the same points in time. That feels like a problem. And so what are we going to do? Well, notice that like acceleration is a very high order object, so we can get away with a bad approximation. So in particular, in leapfrog integration, what we can do is we're going to make the following conceit. We're going to choose ak plus 1. This is where approximation happens, to be f of tk plus 1, yk plus 1. So far, we're good. But the problem is that we need the v at time k plus 1, and we don't have it. So what do you think we're going to do? We're going to cheat. In particular, we're just going to take an average. We'll say, okay, well, this is roughly v. I always get, like, the number 3/2 just looks weird to me, so like I really don't want to write it for some reason. K plus 3/2 plus vk plus 1/2, like that. Make sense? So if you kind of work out the dependency graph of this thing, it's a little bit complicated to convince yourself that you can predict the future using this integrator, right? Like, essentially, it seems like all of these things are sort of jumbled together because of this formula here. And so you have to kind of think a bit about, like, what are the ingredients I need to solve one of these systems? And so typically what ends up happening is that you still advance, I think it's time k plus 1 and time k plus 3/2 at the same time for this integrator. So it's actually implicit because of this formula here. Let's see if we can actually work that out. If you're wondering, I always get this wrong, so we'll see if we can do it together. So, and then we're going to see that there's one really beautiful special case of this integrator where things are particularly clean. All right, so, right, so we have, let's just write a few things here. So let's say we have y1, y2, y3, y4, and now we've got v 3/2. I really don't want to write 3/2. v 5/2, v 7/2, and so on. And then we have a1, a2, a3, a4, right? So let's say that I want to use leapfrog integration in practice, okay? By the way, typically what I'm actually given is like v1, right? So I'll use some stupid integrator like forward Euler for just like one little itty bitty time step at the beginning, and it sort of doesn't count in my error a whole lot because it's not iterated. Okay. So let's think about the dependency graph a bit. So in order to compute, so let's say that this is the information that I have. A1, v3/2, y1, right? Now the question is, what information can I get next? Well, presumably what we're going to try and get are a2, v5/2, and y2, like that, right? That's going to be our integration strategy. Okay. By the way, notice that like we don't really need the a's. The a's are just sort of a function of everything else. But notice that we can actually write a system of equations for y2 and v5/2. Do you see how we're going to do that? So in particular, notice that y2 is equal to y1 plus h v, I guess 3/2, right? And then now we have v 5/2 is going to be equal to v 3/2 plus h. Now we have a2, right? But let's go ahead and plug in what is a2. So it's really f of t2 y2 and then 1/2 v 3/2 plus v 5/2. I hate this stuff. Indices are hard. Okay, here's the thing. There's two equations and there's two unknowns, right? Do you see that? So our two unknowns are y2 and v 5/2, right? Everything else is a constant. We actually know the state of our system at the previous point in time, right? And so in general, leapfrog integration is actually an implicit integrator. You have to solve this system of equation to advance time, right? That's perfectly fine. This is a nice second order integrator. It's a pretty easy one to work with. Now, here's kind of an interesting thing. Oftentimes in physics, we have a really nice property, which is that a lot of forces in physics are not velocity dependent, right? So think about like, I don't know, springs, gravity. What are some other ones? Electro, whatever. I'm not a physicist, sorry. In particular, a lot of forces are what we would call conservative, right? They're just position-based. In that particular case, f no longer depends on its third argument, right? So you can slice that guy out, right? Now do you guys see what happens? Let's think for a second. So that's right. So here's the kind of cool thing. I know y1 and I know v 3/2, right? That's my initial data. So now I can get y2. That's easy enough. Okay. Well, in fact, I guess I should do that. And now, thankfully, well, I've removed the implicit part of my problem. I know v 3/2. I know y2. So I can get v 5/2. Like that. Right? And now I can keep chaining these things together. And so on. Does that make sense? So this is called leapfrog integration, and it is an explicit integrator specifically when f does not depend on velocity. Does that make sense? So this is a really simple formula, and moreover, it's second order accurate. It's also very easy to implement. We'll go Jonah first. Yeah?
Is this something that people would use in its implicit form as well for non-conservative situations?
Yeah, it's a pretty widely used integrator, but it is worth knowing that it's a lot slower in that case. Yes?
Just a clarification. So is it called leapfrog integration only in the explicit case or also in the implicit case?
Oh. I don't know. It depends on your book. I think my book calls it leapfrog. If you're fancy, you can call it Stürmer Verlet, but I wouldn't worry about it. Yes? Oh, then I guess I'm wrong. In my book, leapfrog apparently is only the explicit one. I wouldn't worry about it. We're not going to catch you on terminology. Yes? It is y, yes. So please let me, I keep telling you guys to tell me when there's a typo and I'll fix it after class and nobody ever messages me. There's a typo here. You will help your future students if you actually message me and I remember to fix it. Yeah, that should obviously be a y. My bad. All right, any other stupid mistakes, inconsistencies? Fabulous. So in any event, leapfrog integration, here's a nicer picture. It's exactly what we drew on the board, I think. Yeah. Of how this thing works, and it's specifically for conservative physical systems, which are like, it's a fancy way of saying that basically f doesn't depend on velocity. So you can't have forces like, I don't know, air resistance, wind resistance, or friction, I guess. And basically the whole point here is if you work out the dependency graph of this staggered grid integrator, essentially the implicit part goes away because that's only the first derivative piece of the puzzle. And now you have this kind of fun ping pong thing, which sort of does like the v's on the half time steps and the y on the integer time steps. And it's using that sort of asymmetry are you able to achieve higher order integration. Right? So this is sort of a very different strategy than like what we did last lecture where we got higher order stuff by just doing Taylor series to more terms. That makes sense? Okay. So here's the good news. We're all done with numerical integration. To be absolutely clear, this is like the tip of the iceberg. There are so many numerical integrators out there in the universe. They have different properties. There are different stabilities, accuracy, efficiency. Some of them can serve momentum. Some of them can serve energy. Some of them decay energy at a particular rate that is determined by a physical system with friction. Like you name it, somebody has worked on it. This is a topic that has been around since like the beginning of time. And deriving specialized integrators for physics problems is just like a fun hobby of applied mathematicians. But I think this is enough to have a pretty good grasp on the field. Essentially, I think the very first step in deriving 82% of these things is to write down a bunch of Taylor series, start throwing away terms, and working out the order accuracy that you want. By the way, the remaining, I guess, 18%, usually probably start instead with the Lagrangian, which if you've taken enough physics class is a different way to derive integrator, but in this class we don't have that formality around, so we can't really do that. Any questions so far? Okay, so in the last little bit of, well, this course, I thought I would glue a few topics together. Namely, in the second half of this class, we talked about optimization procedures, and then we talked about numerical differential equations and derivatives and so on. And there's actually a wide class of problems that glues these things together. These are sometimes control problems. They're sometimes like inverse problems in physics and so on, where like, you're trying to work out the initial condition for some system, like, y1 and v1, for example, so that the final conditions of this thing have some particular property, right? And so if you think about it, like the derivative that I'm going to need, like if I have some loss function like L of y25, right? Because like I want it, like I predict the physics in the future, and now I evaluate some property of it. Like, did my basketball end up going through the hoop, right? Would require differentiating through this entire process. And I'm going to motivate this also in a machine learning language in a second, because there's a really interesting set of tools in that domain. But the basic point is that oftentimes it's not enough to just predict the future. You also want to know how the future would change as you change the conditions on your system, right? And this is sort of the tip of a new iceberg. Sometimes we call this sensitivity analysis. And I think it's kind of a fun way to glue together things that we've done, right? If we want to apply, for example, gradient descent to this function L, then we're going to need to learn how to differentiate this thing. Now, there's a lot of different options for computing this derivative. I mean, one of them, for example, is literally like, notice your numerical integrator is complicated, but it's just a bunch of formulas all tangled together. So one thing that a lot of people will do, which is perfectly fine, is to remember all of those formulas and then just compute a giant derivative through all of them. It's systematic. Like basically, for example, if you code your numerical integrator in PyTorch, you can do the dot backward function. It'll remember all of the steps of your time integration, and then it'll give you back the derivative. You have to be careful. It's an approximation. It's a derivative of the result of your numerical integrator, which is not always the same as your physics, but often pretty close. But I thought it would be kind of fun to cover a different strategy. I would say every 2 years becomes popular, and then every other 2 years, like it's like people go back to differentiating through their solver. I mean, there's advantages and disadvantages to both. I think, for example, if you just differentiate through this giant formula here, you have to remember all the steps. And if you have a really stiff numerical problem, remember, stiff here means like probably highly oscillatory, right? Then you probably have a ton of steps you got to differentiate through, which is quite expensive. And so in that particular regime, a lot of times a good question you might ask is, can I get my derivative in some other fashion, right? And as another hint, notice that the derivative I really wanted was not of my solver, it was of the ODE itself, which I don't really have access to. So I've already made a lot of approximations, okay? And that's going to lead us to a different strategy called the adjoint method. I don't have slides on this thing, sorry. I got bored. I stopped making slides. I'm tired. It's the end of the semester. Okay. But that's okay, because the reality is we haven't really relied on the slides very much in this class anyway. Okay. If you're curious, this is not just a physics thing, but also is a very popular tool in machine learning. In particular, I thought I'd quickly motivate one of the applications of this machinery. Good. We've got an hour. That's about what I need. Which is as follows. So these days, if I've learned anything from the MIT College of Computing, it's that I should be caring about generative AI. And in particular, there's a class of generative machine learning problems that falls very cleanly into the types of things that we'll talk about. This is a set of machinery. Sometimes in the community, they're called continuous normalizing flows. I think this is one of these ideas, as with many, that like sort of is in the water when it came out. There were a lot of different papers that all claim different pieces of ownership to these ideas. I'm not going to claim to understand and do attribution properly. I think oftentimes it's attributed to Chen et al. But the reality is that there's like a lot of different things that kind of came out roughly at the same time as this research paper. So rather than trying to do all this storytelling, there's a fantastic survey out there. When I say fantastic, I mean like for people like me. So it's like mathy. It's not just like a fun list of software tools. That is by, let's see, Papa Makarios. Hopefully I'm spelling that correctly. Et al. In 2021. And this was in the Journal of Machine Learning Research. So essentially, there's a lot of problems in machine learning, AI, statistics, whatever you want to call it, that are in the universe of generative modeling. It essentially says the following. I have a big data set that's sampled from some really complicated distributions. So think about like I go out on the internet and I collect a lot of photographs. I think is the typical example. Although it turns out that like implementation details in that regime make the math that we're talking about here a little bit questionable. You can talk to my student Chris about that. But in any event, we go out, we collect this whole data set, and we have this model, which is that data is sampled from some probability distribution over that space. So in other words, there's like some density function that exists in the world of n by n grids of numbers, which are representing photographs, and the density is large when that thing actually looks like a photo, and it's low when it doesn't, right? And if you think about generative AI from like a really reductive mathematical perspective, what is it trying to do? You get a bunch of samples from that distribution, and now you're trying to generate new things that look like samples from that distribution. The only problem is it's a really complicated distribution, okay? So that's the sort of motivation. In this particular domain, here's a kind of interesting way to think about it. This motivates a lot of generative tools, by the way. Computers are really good at generating random numbers, or pseudo-random numbers at least. But they're really bad at generating ones that are distributed like photographs. What they are pretty good at is like drawing things that look like bell curves. That's okay. In particular, like what we can do is maybe draw some variable, I'm going to call it u here, from some simple class of probability distributions like p psi. So think about this as like normal distributions centered at 0, or maybe psi here is like the standard deviation or something like that. So there's this class of things the computer knows how to sample from, right? Or even simpler, like uniform random numbers between 0 and 1. Perfectly fine. Okay? So then you can understand a lot of these really fancy machine learning architectures. Like at the end of the day, this is all your like numerical code knows how to do. It doesn't know how to draw images. It just knows how to draw Gaussian stuff, right? And so one strategy for making a complicated generative tool, so let's say this is the space of photographs, which we all know is bimodal, is to basically learn a mapping t theta, which inputs a Gaussian random variable, and then kind of reshapes that space to be distributed some other way, right? So in particular, then, we have some sample x that is going to be t theta of u, and the distribution of x could be really complicated. So for example, the function t theta here probably takes mass from this bell curve and like kind of bunches it up like that. Does this schematic make sense to you guys? Okay. And now t theta could be super complicated. It could be a neural network, whatever. Okay. Now, in general, we are going to make a conceit in this particular corner of generative machine learning stuff, which is that what we would like is for t theta to be an invertible map. And the reason for that is that then we can do a lot of things that relate the distribution of x's to the distribution of u's and vice versa. So for example, it's easy enough to write the density function of x by kind of looking at the derivative of t theta, right? Because t theta, like when the derivative is big, then it's kind of stretching stuff out. When the derivative is small, it's kind of squashing it together. But if this is not an invertible map, then we could run into trouble where like t theta takes two different regions of the space and maps it onto the same part, in which case it's no longer a calculus problem to work out density. You have to like figure out all the different pre-images. Does that make sense? And so in particular, here's a kind of nice formula. And it's kind of cool. So long as t theta is closed form, one question we might ask is, can we get the density function of x? Like, what is the likelihood? So if I choose some point here, like what is the fraction of samples u that are going to end up somewhere close to x, informally speaking? And the good news is there's a nice formula for this. It's just a byproduct of the integral change of variables formula from calculus class, right? So if you remember, or u substitution in one variable. which basically says that this is p psi of u, where u is the pre-image of x under this map, times the absolute value of the determinant of the Jacobian of t theta evaluated at u inverse. All right, let's sanity check this thing real quick. So if we don't like j or d or whatever, we can also just think in one variable, right? So in that case, that's just the derivative of this t theta map. And think about it this way. If the t theta has a big derivative, right, it's got a high velocity, what does that mean? That means nearby samples x end up kind of far apart down here, right, because the velocity is really large, so the function is changing rapidly. So in that case, you would expect the density here to be lower than the density there, right? It is taking samples and spreading them apart. Does that intuition make sense? So that's where this inverse comes from, okay? Of course, in one variable, determinant of a 1-by-1 matrix is a thing I think we could all compute. You guys are killing me. Look like you're gonna die. Please help me out. Okay, so essentially, here's a lot of generative machine learning in one very reductive picture. This is follows. We have some really complicated distribution, like in this case, the distribution of natural photographs. We obviously don't have access to that, but we can kind of sample from it. You see that? We can go on the internet, we can download a lot of photos. I spent like all morning doing this on Instagram. And so if we do that, a question we might ask is, can we formulate a loss function that kind of like randomly draws stuff from p of x, has random samples from the actual distribution, and then tries to bring them closer in some fashion or another? Does that make sense? And there's like so many different ways to do this. Turns out I wrote a whole PhD thesis on one, but that one's too complicated, so we're gonna do a simpler one. And that is one that I think is popular in a lot of corners of machine learning, mostly because it's easy, which is easy is good. Like these are hard problems, which is to minimize a particular notion of distance. Now, in particular, we have two different distributions we're going to work with. One of them is a distribution we don't have access to, which we're going to call p star, which maybe we'll call data generating distribution. And this is like the distribution over all photographs in the world, right? But what we do have access to is our like little sad p of x, which is what our computer's trying to do. And in some sense, we're trying to bring these two things close to each other, right? In other words, we want the things that my computer generates to look like images out there in the wild, right? And so one thing that we can do is try to minimize some notion of distance between p star and p of x. There's many distances out there. My particular favorite is Wasserstein. In this class, we're going to talk about one called KL divergence, which you may have, like if you've taken a probability class, you've probably seen. So here's what the KL divergence is going to do. So in general, by the way, KL stands for Kullback-Leibler. I can never pronounce it correctly. By the way, in optimization, there's a different KL. It's like Kurdyka-Lojasevics or something like that. It's not that KL. This is the probability KL. Okay. KL divergence is a very simple notion of relating two probability densities to one another. It looks like the following. The integral p of x log p of x over q of x. KL divergence has a lot of really nice properties. So for example, if I minimize KL divergence over p with q fixed, then the minimum is just q, which is good. So like it's some notion of distance. You have to be careful using the word distance here, because the one thing that KL divergence is not is symmetric. If you take information theory course, you'll come up with all kinds of beautiful interpretations of this thing. I think roughly, I always get it backward. I think it's like an estimate of the number of bits it takes to approximate a sample from P using a sample from Q or vice versa. I always get this wrong. I don't know. Doesn't really matter. For my purposes, it's a number that's small when these things are similar. Okay? Cool. I'm an optimization person, not a probability person. Okay. Now, if you read a lot of machine learning treatments of this function, I think people they wax very philosophical about this thing. And in particular, here's the thing we might do. We might put like p star, like our data distribution, as one of these two arguments, and then p of x as the other, and try to minimize. Right? I think that's a totally reasonable strategy. I think a good question is which one is which. You can read all kinds of philosophy about which one you should put in which argument. Like if you, that Bayesian in the classroom is nodding. But I think the reality is we do the one that makes the math easier. And then we all try to convince ourselves a posteriori that that was the right one all along. Like I truly believe that if the math were easier the other way, then Bayesians would come up with a reason why that was actually the right answer. Don't tell your advisor I said that. Okay. So let's see if we can figure that out. Namely, even if I've lost you with all this probability, what is the log of x over y? That's right. So we have, this is the integral of, oops, wrong class. This is a p of x. We don't have any continuity equations yet. Give me another hour and we'll do that. Minus the integral p of x log q of x. Okay. Now, from this perspective, in general, if I have a function and I integrate it against the probability distribution, I can think of that in a nice kind of probabilistic way. That's like I draw samples that are distributed like p, and then I take the average value of whatever's next to it, right? This is called an expectation. And so in particular, I can write this a different way. I can say this is the expectation where I randomly draw x from p of log p of x minus log q of x. In fact, actually, maybe to make it even more obvious, right, there's two integrals here, so I can even do minus the expectation over the same x of log q of x. Cool? Now this gives us a hint as to what direction we should put our KL divergence. In particular, do I have the density function of the set of natural images? That would be a very complicated thing, right? You guys see that? So in particular, do I really want to evaluate log p of x where p is like the likelihood of observing a photograph on the internet? Probably not, right? And so from this perspective, I think it's pretty clear our optimization variable should try to make this thing a constant in our problem. And so from that perspective, I think now we can kind of see that, on the other hand, we are good at sampling photographs from the internet. So probably that's where we should stick our data distribution. That makes sense? And so in particular, what that allows us to do is to say, okay, here's going to be our loss. So we've got some set of maps. I haven't told you what they are so far, but I'm going to think of theta as just a bunch of parameters, like the neural network weights, that tell me how to map u's to x's. Cool? Then I can think of a loss function, L of theta. You might notice the difficulty of this lecture jumped up about 3 levels from the last one, sorry. Which is going to be the KL divergence between the data generating distribution and p theta, which is the thing that my computer knows how to generate. Does that make sense? And in particular, when I do that, this term becomes a constant minus, and now we have the expectation over x drawn from p star of log p theta of x. Why is this a good thing? So let's think about what this is doing in just words for a second, okay? How do I actually compute expectations? I randomly draw stuff, and then I evaluate the thing in the inside, and I take an average. That's what this notation is saying. It's saying randomly draw a bunch of x's, evaluate this number at each of those x's, and then just average the values together. Okay? So think about what this means in code. Essentially, I go out on the internet, I download a bunch of photographs, and now I have my potential machine learning model, p theta. I evaluate, does my machine learning model think that the images I downloaded from the internet are likely or not? And that's basically my loss, up to a log factor. So the good news is, like, even just intuitively, this feels like the right thing to do. Does that make sense? Okay. Yes? Yeah. So, sorry. I've inserted a theta here because the map t theta is going to be the thing that generates it. Good catch. Yeah. Okay. Now, all of this is mostly motivation for the calculation we're going to do. But in particular, here's a kind of fun thing. So remember, we already have a nice formula for, you're right. Sorry, p theta. By the way, this I guess really is p theta psi, but we can even assume psi is a constant. Like for instance, the standard Gaussian is perfectly fine here. But I say, aha, we actually just have a formula for p theta, so this is pretty nice. This loss is really some constant minus the expectation over x of, oh no, my notes, there it is, log p psi of t theta inverse of x, remember that's u, plus log of the determinant t, jt theta inverse. And this is just this formula copied with the log. Cool? Now here's the good news. We actually have access to all of these things. So in particular, if t is an invertible map, then like we can get the u. It might be complicated, but we can get it, right? And this is actually a loss function we can evaluate, right? And so there's a lot of like generative models out there that really just do train this loss function. And basically the ingredients that you're going to need for that are a few. Like I need the inverse map, right? I need to be able to take x's and map them back to their pre-images u. Think about what that is in words. That's like what Gaussian random variable would have led to this image under my map, right? And moreover, I need to evaluate the derivative of that map. Cool? Okay. So this is a really clever little trick. I mean, essentially notice that we've really carefully designed our loss function so that we just need samples from a data set and then likelihoods from our model and not the other way around, because then we'd be in trouble. Yeah? Okay. And so what we need, what is our missing ingredient? In some sense, what we need to figure out is like, what is a nice class of maps t theta, right? Like, how do I actually put an invertible map on a computer? And it turns out that ordinary differential equation theory provides a really nice answer to that. Now, here's going to be the idea of a continuous normalizing flow. This, by the way, is kind of a fun link. Like if you take a class in differential topology, this is a link between topology and vector fields. So here's a cool thing we can do. We just spent the last couple lectures solving differential equations. You guys knew this was coming. In a continuous normalizing flow, we're going to say that our map from u's to x's is given by the solution of a differential equation. This feels complicated because it is, but on the other hand, it turns out to have some really beautiful properties. So in particular, the continuous normalizing flow idea is going to be the following. We're going to learn, but in quotation marks learn, it's really optimized for, a function g theta of t comma z, where t is going to be between 0 and 1, like that. And here, g is going to map from Rn to Rn. So it like acts on the space of x's here. And the way that we can think about it is following. We're going to solve an ordinary differential equation. dz dt is equal to g theta of tz, like that, with z of 0 equal to u. So let's pause for a second and make sure we understand. So g theta is going to be like a neural network, or just some generic class of functions with a bunch of parameters theta. So think of theta like the weights of a neural network, or if you want like a bunch of coefficients in front of a polynomial interpolant, it's perfectly fine for this class. And it takes two inputs. It takes in a time t and a point in space, okay? And what it outputs is a vector, which is going to give the rate of change of z, okay? So the basic idea here is that basically in this picture, rather than making a map t theta which jumps directly from the initial distribution to the final one, we're going to make a map that's kind of incremental. It like takes a point here, and then like maybe scoots it out a little bit, and then scoots it out a little more. So essentially we're putting little tangents everywhere in this time between 0 and 1, which are going to flow samples from time 0 to time 1 to give us our map. Does that make sense? Now, the question is, why the heck would we do that? It feels awfully complicated, right? I mean, a different thing we could do might be to parameterize t theta as just like a neural network, just a map that inputs a point and outputs a point. Like, why are we bothering with this ODE? Now, the reason for that is that we need t theta to be invertible for all this math to work out, right? And in general, like a generic function is not invertible, right? Like f of x equals 0 is a good example of a non-invertible function that can be very easily written as a neural network, yeah? Here's the kind of beautiful property, one that we actually didn't state in the slides of this course, but is absolutely the case. The map from your system at t equals 0 to the system at t equals 1, like the solution map of my ODE, that thing is a diffeomorphism. It actually is an invertible map. In fact, this is actually not so hard to prove. So here's a way you can do it. So let's look at z at time 1 by the fundamental theorem of calculus. This is z at time 0 plus an integral from 0 to 1 of g t. Because remember that this thing by definition is dz dt, like that. So I can actually just rearrange this expression ever so slightly. So notice that I can do the following. Right? I can say, okay, well in that case, z of 0 is z of 1 minus the integral from 0 to 1 of g theta t z of t. You guys follow the advanced argument here? Okay, and let me make it even more complicated. 1 plus the integral from 1 to 0 of g theta t. Now, if we read this formula spiritually, what is it saying? It's saying the following. If I solve my ordinary differential equation starting at time 0 and going to time 1 through vector field g, right? Remember, vector field g is like these little tangents over here. Now, if I take the result of that, and I do exactly the reverse process. I flip the sign of my vector field, I change all my velocities to just move backward, and I just run time in reverse, I ended up back where I started, right? And because of that property, essentially our mapping from z0 to z1 is a diffeomorphism. There's exactly one z1 for every z0. And that's exactly the property that we wanted, okay? This idea, by the way, of just using this to parameterize invertible maps also relates to this idea of neural ordinary differential equation. I think technically the neural ODE people did not, the very first paper in this domain wasn't really using the diffeomorphism property. It was just using it to learn ODEs. I think. Don't quote me on that. Okay. Moreover, one fact that we're going to prove we're going to state without proving, and then we're going to do real math for the rest of this lecture, is as follows. Here's a kind of interesting thing. Notice that it makes perfect sense to talk about probability distribution like pt of z, which is the likelihood of observing a z at time t, right? So for example, p0 of z is just like our generating distribution. In fact, maybe let's just write it without the z's. P0 so in other words, at time 0, our data is just distributed like the thing that our computer knows how to draw, right? At time 1, it's distributed in some complicated fashion. But in particular, here's a kind of fun formula I'll let you guys think about at home, which is if I look at d of the log of p at z of t dt. It's a complicated expression, but like let's think about what it's saying. It's saying what is the change in likelihood of my sample as it kind of floats around. So it has to do with that like determinant factor there. One thing you can prove is it's minus the trace of the derivative of our map g. Now, this doesn't matter a whole lot except that essentially my point here is that if we can just compute derivatives into our ODE solvers, there's like a lot of really nice things that we can do. And so for example, if I want to evaluate the likelihood of z of 1, if I solve the ODE, right, so I get this path of z's from time 0 to time 1, I can compute the likelihood at time 0, and now I can integrate a second ODE forward in time to figure out the likelihood at time 1. Right? So there's all kinds of really nice things that happen here. Now, essentially, by the way, this trace is kind of expensive for high-dimensional problems. There's something called a Hutchinson trace estimator, which is like a really bad way to do this randomly, but we'll save that for another day. Okay. Have I managed to lose you all yet? Because I'm trying pretty hard. So quiet. All right. Then I'm going to keep going. So essentially, here's my point. In a lot of these different problems, including both neural ODE and a lot of problems in physics, we have exactly the same situation, where I have some differential equation that's solving some dynamical problem, right? So for example, in neural ODE, it's the mapping from samples of my boring distribution to samples of my interesting distribution. Or in physics, it's maybe the mapping from like my physical system at time 0 to time 1. And then essentially, I want to evaluate some property of the thing at time 1. So for example, this like KL divergence we wrote before, or like, did my basketball go through the hoop? And what I need is to be able to differentiate through that ODE to actually be able to optimize our loss. So in other words, what we need, in some sense, is d loss d theta. By the way, for now, let's just think of theta as one variable. Everything is going to carry over to gradients. I just don't feel like doing fancy calculus in addition to all this mess. OK. And there's like basically two different options that people typically use for this problem. One of them is to backpropagate through your solver. So for example, maybe I solved the ODE at the top of the slide using forward Euler, right? Which if you think about it is just evaluating G a bunch of times to advance forward in time. I remember all and I think of that as just one giant formula for getting the system at time 1 from time 0. Then I could compute one giant derivative. And that's perfectly fine, but it's an awfully complicated derivative, right? You're going to have to remember a lot of steps. And moreover, if you really want to solve this system well, you have a really tiny h, then the expense of that can get really high. Yeah? So there's a second strategy, which has its own drawbacks, for sure. But we're going to derive it because it's kind of fun, called the adjoint method, which makes a really beautiful observation. This is so cool. Like, this is one of these things that just feels like it's too good to be true, which says the following. I'm going to be able to work out an interesting way to compute derivatives of one of these solvers by solving a second differential equation after solving the first one. This is totally surprising. OK. So let's see if we can abstract our problem just a little bit, because I think this is like a hot mess that I just illustrated. By the way, this is mostly just motivation. The good news is you can pause here. Now I'm going to write down an abstract math problem, and you can map it onto whatever problem you wish, which is as follows. Let's say that I have an ODE, which is going to be y prime equals f. And now we're going to think of it abstractly, like t, y, and we're going to add like one little spicy note to our problem, which is a parameter theta. Right? So think about like I have f equals ma, and I can vary the stiffness of a spring, right? And every different stiffness leads me to a different differential equation that I want to solve, right? Like springs oscillate more quickly when they're stiff. Then I would put like the parameter, like the stiffness there. Yeah? Or the more fancy version of this is I put all the neural network parameters for my neural ODE stuff, all hide in this theta thing. We're going to think of theta as one-dimensional because the math doesn't matter and I just don't feel like writing curly Ds. OK. Moreover, just for simplicity, let's assume for now that I prescribe y naught. Right? So think about, like, again, mapping onto our physics. I'm going to keep trying to map this onto intuition. Think about our physics problem. I always pull my spring out to the same distance and let it go. And then my optimization variable is I would like my wobbly spring to be at this location at time 3. OK? So that's the kind of problem we're going to be able to solve. Everybody with me in my setup so far? OK. So I'm going to make a loss function, L of theta, of a nice form. This form, there are a lot of different forms out there, but whatever. I'm going to write as an integral from 0 to 1. I'm noticing my notation clashes a little bit. Do I want to fix it on the fly, or do I want to stick with my notes? I'm going to stick with my note. No, I'm not. I'm going to... Yeah, I'm going to stick with my notes. In particular, the letter G used to be a vector field. I'm so sorry. I'm going to use it for loss function. Is everybody OK with that? We're going to forget everything at the top here, just to make you a little more confused. In particular, G is now a function that inputs t, y of t, and maybe even theta dt. So think about this thing. So like I'm doing my physics forward in time. I get the solution of my ODE, which is y. And at different points in time, I can like evaluate different properties. So like maybe I like really want at like time 0.5 to be close to some location or something like that. OK? All right. So the kinds of optimization problems that I'm going to want to solve are going to look like the following. In some sense, min theta of the loss of theta. But what I can do is add a variable, which is like a function, y of t, with the following properties, subject to y prime equals f t y theta, just like before, and y0 equals y0. Okay, so do you guys all agree with me that this little kind of abstraction here encapsulates all the problems we've talked about? So notice that there's secretly two variables, and one of them is really hard to work with, right? So we're used to thinking about problems where our loss involves like a parameter, but now we also have an unknown function y of t. Yes?
And the problem we cared about, isn't the loss only defined at the final time step?
That's right. So if the loss is only defined at the final time step, then maybe I put a giant weight in front of g at time 1. In fact, you can even stick a delta function there if you want to. This formula encapsulates a lot of different losses. That's a good question. Yeah. Any other? Fabulous. So here's going to be our goal for the rest of lecture today. I think we can do it. Is to compute dl d theta. Yes?
Why don't we integrate from 0 to 1?
Oh, that's like totally arbitrary. Like essentially, this is a stand-in for a solution of ODE for some period of time. You can always rescale t to be 0, 1. Yeah. Okay. Now, a little bit of final exam review. You have a problem with constraints. What is the very first thing you should do to understand that problem? Yeah, KKT conditions is right. Or in this particular case, there's no inequality constraint. So you should work out the Lagrange multiplier condition, right? And that's exactly what we're going to do here. But we've got like this kind of weird spicy twist here, which is we've got a variable y of t where there's like a lot of variables. There's a different unknown y for every single t. Do you see that? So like, if you think about it, how many Lagrange multipliers we're going to need? We're going to need one for every single t. Yeah? This is just our fun little twist for the very last lecture of this class. Okay. So, we can do it. So let's like not think too hard and try to write down a Lagrangian. And by the way, one interesting thing about adjoint method, we're going to write down the Lagrangian, but we're not going to write its critical point condition because that turns out to be not the thing we care about. We want dl d theta. We don't just want to know what happens at the minimum. But it turns out Lagrangians have a lot of nice properties. So in particular, here's a Lagrangian. And it's a function of a lot of stuff. In particular, it's a function of our unknown variables. And we're going to have to add a Lagrange multiplier, which is actually a function, lambda of t, because it has to enforce a different constraint at every single t. Do you guys see that? So at least abstractly, we can do the following. We can write our Lagrangian, which is always the objective function. So this is g of t, y of t, theta dt minus, and now remember, like, what is the Lagrangian? Like abstractly, it's the dot product between the Lagrange multiplier and the constraint. So in this case, our dot product is going to be a little abstract. It'll be an integral from 0 to 1 of lambda of t dot product times the constraint, which is y prime equals f of all this stuff. Yeah. T minus f of t y of t theta dt. Cool? This is basically the one interesting new part of this lecture, is the fact that if I have an infinite number of variables, then the dot product that usually happens to Lagrangian now becomes an integral. Okay, we've actually seen this in this class a few times kind of quietly. Okay, yes?
Why don't you need to incorporate the y of 0?
Oh, that's a good question. You could, yeah, that's perfectly fine. We're instead going to do a different thing you can do when you have a constraint like that is kind of just remove the constraint. So in other words, only think of taking derivatives in the class of y's where y of 0 doesn't change.
Okay.
That's what we're going to do here. But certainly for now, we can at least define this thing, and I'll be careful. Anytime I use that property, I'm going to be careful to call it out. Okay. So remember what we want. At the end of the day, we want dl d theta. That's what we're after, right? And so here's kind of what we don't want to do is just take the derivative of this thing and set it equal to 0. And that's a good thing because we don't have the machinery for that in this class. Like we don't even know what does it mean to differentiate this thing with respect to lambda as a whole can of worms we're not going to get into. Okay? But we can still use this as a convenient function. And it turns out that's going to be enough for us to compute the derivative we want. Now, in general, in life, this is just a good life philosophy, also good for midterm. final exams, whatever. Anytime I see a quantity which is an integral of two things multiplied and one of them is differentiated, this is like screaming out for me to do something. Integration by parts, or U substitution, or whatever. Notice that I have a lambda times a y prime, right? So in particular, this thing is equal to the following. I have to be a little careful because there's a minus sign here. So this is minus. By the way, I'm going to stop writing the t's, like lambda of t and y of t. So we're going to have lambda y from 0 to 1, right? Meaning that you just evaluate at those 2 points in time, minus the integral from 0 to 1 of, and we're going to end up with 3 terms, right? We've got this guy from before, so g of t, y, theta, like that. And now we have 2 additional things. So for one, we've now popped the derivative on the other guy, right? That's what integration by parts does. So we now have got, is it a minus or a plus? I always get this wrong. That should be a plus, right? This sign. Yeah. Is that right? Yeah, the sign flips in the integral and you integrate by parts. Right, so this is going to be lambda prime times y. Whew. Sorry, I get caught up in the dumb stuff. Also because I jammed this entire lecture onto 1 page of paper, which was a mistake in retrospect. Okay, plus we have a lambda dot product, oops, a minus, I guess. The good news is all these signs aren't going to matter a ton. F of t, y, theta. All this is integrated dt. Okay, everybody agree with me? Yes. Yes, you're right. Yeah, there should be. Wait a second. Yeah, plus g plus lambda minus. Okay, now we're good. Thank you. Okay. Now, this is an object that I can define, by the way. This Lagrangian is a function that can input whatever it wants. It can input any theta, any y, and any lambda, and this equality is always true. It has nothing to do with being at the minimum. Does that make sense? It's just like a nice function to work with. And so what we're going to do is choose a really sneaky lambda. And that's what's going to define the adjoint method. Okay? So in particular, let's say that I just, yes? Yeah, that's a plus. Fine. You win this time. Okay. You're checking for sign mistakes on your final exam, though. Okay. Yeah, that's right. So up to sign, this expression is true. So someday when you use this in your code, you should check all my math mistakes. Okay. So here's a cool thing. This is true for any lambda. I can literally choose any lambda, and this last equality we just wrote down is true. Right? It actually has nothing to do with optimality. So what we're going to do is choose a really sneaky choice of lambda that's going to make our calculation of dl d theta as clean as possible. Now, in particular, here's what we're going to do. Suppose y of t satisfies the ODE, like that. Then, what happens here? What is the second integral equal to in that case? Remember that our ODE is y prime equals f of y and theta. So clearly, if y satisfies the ODE, the second term doesn't do anything, right? So in that particular case, then we have that our Lagrangian theta y lambda is actually equal to our loss L of theta. This is the sneaky trick. And notice, again, just to keep emphasizing, this is true for any lambda, right? Everybody with me so far? Because this is basically our one little mathematical sleight of hand. Okay. So what does that mean? Well, that means in particular, what is dl d theta? Well, it's exactly the same as d Lagrangian d theta, like that. So far it feels like we're doing something really stupid, right? Like we want to optimize L. I've now introduced this like weirdly complicated thing. And I'm going to differentiate that thing with respect to lambda instead of our original guy. Notice, by the way, that y has theta dependence, right? Because as I noodle around with theta, our ODE changes. Does that make sense? Okay. Hold on, I promise we're almost done. Okay. What is this derivative? Let's see, I need to keep at least of this much visible here. Okay. So in particular, get excited, it's kind of ugly. But it's basically just ugly because we're not canceling things we're about to cancel. Okay, so I'm going to hold lambda constant, but I'm going to vary theta, which means that y is going to change too in response to that, right? Because my ODE is changing. So in particular, I will get minus lambda of 1 dy d theta of 1, right? Plus lambda of 0 dy d theta of 0, right? That's the derivative of this first term here. Okay, now we have got 3 more terms to differentiate. Okay, so we're going to have plus the integral from 0 to 1. Now, what is the integral of this with respect to theta? You have to be the tiniest bit careful because y also has theta dependence. Okay, so in particular, you will have that this is oops, I skipped a line. dg d theta plus dg dy d theta, like that. Right, this is the chain rule. Because again, both of these inputs have theta dependence, so when I differentiate, I get 2 terms when I take the derivative. Okay, so that's term 1. Plus, we've got term 2, which is dy d theta. Sorry, I keep losing my place in my notes. Yeah. Dot product with lambda prime. Right, that's just differentiating the second guy with respect to theta. And finally, we do the same thing with the third, but we have to be careful again because f has 2 different things that depend on theta. So we have lambda inner product with d f dy d theta plus df d theta. Okay. Hopefully I haven't totally lost you guys. What I did is I took this expression and I differentiated with respect to theta. And the problem is that y has theta dependence. So every single time I differentiate the first and the third term, I end up with 2 things. One is df dy d theta, and the other is just df d theta, right? That's what this thing is doing. Cool? All right. Now we are 85% of the way done. Okay. In particular, notice we have a dy d theta here, and we've got a dy d theta there. Okay? So we're going to just regroup this expression. I got 5 minutes. I think we can do it. Basically, this is one of those things where like suddenly the smoke clears, you get a nice expression, and you're done. So this thing, in fact, remember that this is true for any lambda of t. So one thing we can do is start putting properties that we want on lambda of t to make this expression cleaner. In particular, what we can do is choose lambda to satisfy the following property. We can say choose lambda of t with the property that lambda of 1 is equal to 0. Because I can do anything I want. So I'm going to choose that particular lambda, and that is going to 0 out the second term here. Moreover, the first term, dy d theta, sorry. Oh, yeah. Sorry, that zeroes out the first term. The second term, what is dy d theta at time 0? Well, remember that y of time 0, to go back to Zachary's question, is always the same thing, right? So what is dy d theta? Does it have any dependence? No. So both of those first 2 terms are equal to 0. Okay? So we are left with just this integral term from 0 to 1. And let's just regroup this thing ever so slightly. In particular, we're going to isolate the inner product of dy d theta. We've got a dg dy. I'm being a little bit sloppy about dot products, but that's sort of okay. And then we have the dot product between lambda and df dy over there. Right, so we have lambda prime. Right, so we have a dy d theta right here with a lambda prime next to it. And we got a dy d theta there with lambda dot df dy, right? Like that. Lambda. Okay, so here I've grouped all three of those terms together, plus dg d theta plus lambda dot product df d theta. That's basically just everything that's left. Okay, so all I did is I took the integral up there and I just regrouped it. I isolated everything with the dy d theta into one shot. Now I claim we're done. Doesn't look like it. Here's the really cool thing we can do. We are going, remember that this expression is true for any lambda. I can choose any lambda that I want. Moreover, these two terms are actually going to be fairly computable. If I know lambda in time, then notice that these two things are just derivatives of my function without time dependence anymore. So it would be really convenient if this term were 0. So here's what I'm going to do. We are going to choose lambda to solve an ordinary differential equation, which is lambda prime equals minus all this stuff, minus dg dy minus df dy lambda. This is an ODE for lambda. So here's the beautiful thing about the adjoint method. That goes to 0. So in practice, how do I differentiate? When the smoke clears a little bit here, you should repeat this calculation at home because obviously I've gotten myself a tiny bit confused. Only a tiny bit. Now, I wanted my d loss d theta. I originally compute my loss by simulating y forward in time, right? I can do that. That doesn't require any derivative at all. So I actually have y for all of t. That's perfectly fine. Now I evaluate my loss, right? So that's basically in terms of y of t, which I have access to, so that's fine. So the only thing that I'm missing is the derivative. Here's the really beautiful thing that happens in the adjoint method. I now solve a second differential equation for a function lambda. And I actually do it in reverse time, by the way. I start at time equals 1, and I go backward to solve this expression here. And basically, you can think of this as choosing the lambda that zeroes out the inconvenient term in my integral. That's really all it's doing. And the good news is the right-hand side of this expression only depends on lambda and stuff that we got in the forward pass. Like abstractly, that's what to know. Now that I have lambda just by solving an ODE a second time, I can evaluate this integral to get my derivative, which is just the sum. This is just a big dot product. And this is called the adjoint method. It's really beautiful because essentially, rather than having to differentiate through your ODE solver, instead what you do is you solve everything forward, you solve a second thing backward, and then you just assemble them all together into one big derivative formula. In fact, you don't even have to use the same time step for the lambda problem as for the y's. Yeah? And so if you go back and you dig through these neural ODE papers, that's essentially all that's going on, is rather than keeping around a million different links in your computation chain for your integrator, it just solves a second ODE and then extracts a derivative from this thing. So at the end of the day, what does this thing do? It links together all the tools we talked about in the second half of this class. There are 2 different ODE solvers. Then you can take this dl d theta and you can put it in your favorite gradient descent tool to actually solve your inverse problem. Cool? All right, guys. Anyway, this is a big, messy pile of math. I'll let you guys decompress from that later. But hopefully you guys can see this was just the tip of really, really nice iceberg. You guys now have the tools to derive really modern techniques, both in machine learning and in physics. By the way, the adjoint method really goes back to physics, and then machine learning community kind of rediscovered it. And yeah, I hope you continue to study stuff in this area. Numerical analysis is ridiculously fun, huge discipline in computation and mathematics, and there's no shortage of interesting places to go from here. I would encourage you to look into classes on partial differential equations if you like this kind of stuff, or in optimization, convex optimization, and so on if you like the sort of other third of this course, or in fast linear algebra if you like the first part. So with that, thank you very much for your time. Good luck with your final exams. Please do not forget to show up next Thursday, and I will be seeing you from the front of the room. All right. Thank you.